On September 1st last year, a team of 16 scientists published a paper that shook the foundations of what we know about the universe. They observed distant galaxies with the James Webb Space Telescope and discovered something utterly surprising. The common understanding was that the universe underwent rapid expansion before cooling down. Then, the first stars and galaxies started to form during a time we called the Dark Ages. But here's where scientists started scratching their heads. These ancient galaxies looked as developed as our own Milky Way. It's even much more mature than astronomers anticipated, which could only mean one thing, that they must have existed way before our galaxy. Now, why is that a big deal? Apparently, this finding of ancient galaxies is going to challenge our understanding of how the universe began. There is a Big Bang, but the Big Bang was not the beginning. People tend to think that if you have a model in which it keeps on going in some sense and your Big Bang is not the beginning, then you've got to collapse back. So, a fundamental question arises: is it time to reconsider what we think we know about the Big Bang and the origin of time? Before the early 1900s, most scientists thought the universe was static and unchanging. It meant no expansion, no contraction, or any other changes taking place. But all that changed about a century ago. Astronomer Vesto Slipher noticed some nebulae were moving away rapidly. He first thought it was because of our galaxy's motion, but more observations from the Lowell Observatory in Arizona didn't support this idea. That's when Edwin Hubble stepped in. He showed a clear pattern, that the farther away a nebula was, the faster it moved away from us. And what's more interesting is that these discoveries matched what general relativity predicted, that space-time could stretch or shrink. So, if we trace back the universe's expansion using Einstein's equations, we land on the idea that all space, mass, and energy were once squeezed into a tiny point, a singularity. We often hear that the universe began with this singularity, followed by the explosive Big Bang. If we think about it, the scale of the universe is mind-boggling, and the events just before the Big Bang are still a mystery. Now, if everything started from that point, what existed before it? Was there really nothing, no space or time, before the singularity? In order to understand how the rewinding of time went back billions of years ago, let's consider this scenario. Think of our universe like the surface of a balloon. Here, we have to introduce the concept of scale factor. The scale factor is like a ruler to measure the balloon's size. Right now, our universe is blown up to a certain size, which we call one scale factor. But some time ago, this balloon was only half as big. Now, imagine two dots drawn on this balloon. If we blow it up, the dots move farther apart, and that's the expansion we mean. So, in some future moments, the scale factor for this balloon will be larger than 1. Now think about letting the air out of the balloon slowly. As you do, everything on the surface comes closer together. If you could completely deflate the balloon, you'd have a tiny, flat piece of rubber. This is a bit like the singularity, when the whole universe was very close together, extremely hot and super dense. If you extrapolate those equations back in time and try to predict what the conditions were at earlier times, you come to a moment 14 billion years ago when the temperature and density become infinite. But just when you feel you've grasped this bizarre notion, it turns out the picture might not be so clear. Currently, there's strong evidence suggesting we shouldn't take Einstein's equations all the way back to a singularity. For instance, observations hint at a time just before 10^³ seconds when the universe underwent a superfast expansion known as cosmic inflation. Cosmic inflation offers valuable insights into the universe's expansion on a vast scale. It tells us why the universe looks so consistent and how galaxies came to be. In a way, it solves several puzzles in the Big Bang theory. But still, the singularity is a condition of intense density on a minuscule scale where quantum forces play a vital role. So, just using general relativity alone, we can't fully grasp the phenomenon of singularity. This early rapid expansion helps iron out issues with the Big Bang theory. We might need to rethink this whole Big Bang singularity concept, since it will probably reshape our understanding of cosmic inflation and the beginning of the universe. So, what truly unfolded at the start? It turns out that the peculiar nature of the Big Bang singularity suggests it might not be the whole picture. Mathematical singularities in a physical concept usually raise some eyebrows. They often mean the theory has gaps or has been pushed to its limits. And that's where we stand now. We've rewound the universe using general relativity, but this theory isn't all-encompassing. At the extreme densities and temperatures of the Big Bang singularity, general relativity clashes with quantum mechanics. We're not really sure scientifically that there was a beginning to space and time. In fact, we've been exploring the idea that when you actually replace Einstein's theory with an improved theory of gravity, you'll find that the Big Bang was not the beginning, that there existed space and time beforehand. And, in fact, the key events that created the large-scale structure of the universe and even all the galaxies and stars, all those events actually occurred before the Bang. And we only exist here because of those events. So, Roger Penrose provided us with a new framework of thinking. He asked us to imagine what or who's in this universe eventually. If we fast forward time to infinity, who's in this universe eventually? Not us. The black holes will all have evaporated away by Hawking evaporation. They swallow galactic clusters. What's left in the universe? Pretty well, just photons. The photons reach infinity without realizing anything funny has happened. If you put it like that, infinity in this conformal picture is just like anywhere else. So, let's imagine that matter in the whole universe will eventually be dominated by photons. As you might have realized from relativity, the trouble with photons is that they don't feel the passage of time. Why, you might ask? Let's break it down.